So here's the Blakelock jet SAS system, stability augmentation inner loop, and the outer loop CAS, command augmentation system, which would be autopilot. So we should start with the actuator, and that's just 10 over S plus 10. And notice the minus sign, which we won't use because we're going to put the minus sign with the delta E elevator deflection. In other words, we're going to create the variable minus delta E, a pitch up command. And that will get rid of both minus signs that Blakelock has on the actuator and the aircraft. So what we're going to do here is create the actuator and then the aircraft and multiply them together to get the inner loop, open loop transfer function. And we're going to send that to SISO tool. So it turns out that a gain of 5 on the inner loop will give us the bandwidth of 6 radians per second. And so that's what we'll do. We'll replace the rate gyro with a gain of 5. And that will complete our inner loop. Our inner loop will be shown as right here with theta dot as the output and a gain of 5 in the feedback loop. Now that's shown right here where you see the feedback command is being used to generate the closed loop transfer function. And then we create an outer loop closure, which corresponds to the theta being fed back through the outer loop. And then we have to figure out what gain or compensation is going to going into what's called S-amp over here. So once I get OLTF2, I can go into SISO tool and see how I should change. Well, here's SISO tool, and I can see that as I raise the gain, I'm going to go unstable. So looking for my bandwidth of 6, if I can get pretty close to 6, here's 6.07 at 30 degrees phase margin, and I have a closed loop route pretty close to the j omega axis. So it's going to be tough to get my bandwidth required with the required phase margin of 45 to 60 degrees in this situation. But I can add 45 degrees at 6 using the passive lead compensator. So that's what I'm going to do. I'm going to remember this gain around 31. That'll give me the bandwidth. And then I'll add a passive lead compensator. Now let's see what that's going to do. Here's the passive lead compensator Bodie plot that we've chosen all by itself. So we're going to add the gain and the phase curve to the gain and the phase curve shown here for the open loop of the outer loop system. And we've chosen, of course, we have a gain of 30. That's not shown here. But then we have a break frequency of 6, which is our crossover frequency. So the Bodie plot gain curve will be 0 dB below 6. And then it asymptotically will go up at 20 dB per decade. That's this numerator term, S over 6 plus 1. In the denominator, we have S over 60 plus 1, and that's meant to take out this gain that's going up. And so at 60, the downgoing minus 20 dB will be added to the upgoing plus 20 dB, and it'll be flat again. So the net gain curve is going to be asymptotically shown by the red. The actual curve is shown by the blue. And the goal is not to change the crossover frequency. Now you can see that I've got a 3 dB difference between the asymptote and the actual curve. So if you want to lower this by 3 dB, that's fine. That would make it exactly no change on the crossover. Now the phase, which is why we put this in here, we know the phase is going to go from 0 to plus 90 for the numerator term s over 6 plus 1. And here it is, it's going to be 0 degrees below 10 times lower than 6. So at 0.6, the asymptote will start going towards 90 degrees, right? And when when omega equals 6, you'll have 1 plus J1, or 45 degrees, this point shown right here. Now it doesn't continue going up because in the denominator, I've got this 60. And this 60 is going to start going to minus 90 at 6. So it's going to minus 90. The s over 6 is going to plus 90. And they'll cancel each other, leaving a flat phase angle curve until 60, when this numerator term will have reached 90 degrees. And then only the denominator term will be acting. So at 60, the denominator term will take over until it goes to 600, and at 600, its phase curve will end. The net result is going to be a phase lead between the break frequency that looks like a trapezoid bounded by 45 degrees. Now, if you made these break frequencies at 6 and 60 farther apart, you could raise this trapezoid past 45 until it became a triangle and peaked at 90 degrees. However, that's almost impossible to implement, and so going more than an order of magnitude is not advised. Although we probably could squeeze 60 degrees out of this if we took a double E to maybe the Olive Garden. He'd make one for us to go 60 degrees. So why not put the numerator lead break frequency at crossover? In other words, isn't it always a good idea to put this first break frequency at crossover or near crossover, and maybe put a gain out in front of 1 as shown here, or 3 dB? So if we multiply this form into a more standard form, we see we get 10 times s plus 6 over s plus 60, and as omega goes to 0, you get 10 times 6 over 60, which is 1. So either way, whatever you prefer, I think it's easier to see the break frequencies in this top edge term. So here's the lead being put in. There's the gain of 30, and you can see after the gain of 30 comes the numerator break frequency at 6, and then the denominator break frequency at 60. And then we will multiply the old open loop transfer function, and that was equal to the closed loop inner loop divided by s by the lead, and then we'll end up with this shorthand transfer function seen here. Now, once again, when I change the gain, it looks like gain was reduced to 0.8. I got 6 point. Well, I could reduce it a little bit more to get around 6, and it's hard to do that. So here we are in CISO tool, and we can see that with the compensator, I've got good phase margin, 50 degrees, but my closed loop damping is not following the phase margin in this case. And if I change the gain, I'm going to be moving into the area of instability. So I might want to actually lower the gain to take a phase margin closer to a damping that I'll accept. let's go ahead and try the bandwidth of 6. So I'm going up here to 6. There's a bandwidth of 7. Again, I really don't like what this closed loop pole is doing. But let me get my bandwidth there. There's a bandwidth right at 6 radians a second. Phase margin 72. And let's look at the time response. And it looks like, yeah, if I could take that little blurb overshoot, the steady state output is good, equals the input. I've got a little oscillation here, and that oscillation I'm almost certain is caused by this pole with damping of 0.3 or so. But I've got good phase margin, and that's good protection against phase loss and unmodeled dynamics. And it looks like I even have some gain margin, which we haven't talked about. So that ends this design. If we want to review what we did, here was the initial actuator and airplane. We got rid of these minus signs by attaching them to the variable minus del E for a pitch up command. Then we closed the inner loop, a SAS loop with a gain of 5. And we might want to re-look at that and try to get that loop closer with more damping for the outer loop closure. But we used 5. That loop's going to be always closed, and the pilot will fly that loop. When he hooks up the autopilot, then a switch will be closed, and he'll integrate pitch rate to theta and feed it back to a theta command. And he'll want that theta to be following the theta command. The arrow will go into our compensator, and we designed a compensator that needed some lead at bandwidth of 6 radians per second. So we built a compensator of S over 6 plus 1 divided by S over 60 plus 1, and that gave us a 45-degree lead at 6. So our crossover was good. And we also picked a gain. I don't remember the gain right now, but it was a gain associated with that compensation. So when you close the outer loop, we'd get pretty decent performance, and we would go back to the customer now and negotiate the specifications. So maybe we could make it cheaper if he could take less bandwidth in the outer loop or whatever. You can see it's an iterative process. Yeah, and we just did the first iteration of this design loop. And this ends this video.